Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So this is the 12th lecture of the dynamic programming playlist, and if you remember, we were continuing with the pattern of problems on DP on grids. The first patterns that we solved was from a fixed starting point to a fixed ending point, and in the lecture 11 we did something as a fixed starting point to a variable ending point. So there was a comment which stated, what if it has a variable starting point and a variable ending point? How do you approach such problems? So this is where I thought of solving the next problem, which is the maximum path sum in the matrix. Now what is the problem stating? The problem states you're given an n cross m matrix filled with integer numbers. Okay, now you have to find the maximum sum that can be obtained from a path starting from any cell in the first row. Very important. They're not saying that you have to start from 0 comma 0. They're saying you can start from any cell in the first row and you have to just move till the last row. So any cell in the first row is the starting point, any cell in the last row is the ending point. From a cell in a row you can move to another cell directly below that row, or diagonally left or diagonally right. So from a particular row cell we can move in three directions. Okay, so for an example, like if you see this matrix, they're saying that if you start from 2, like you can start from 1 2 10 4, whichever you wish to, but if you start from 2 then you go to 11, then you go to 1, then you go to 2, this is the maximum that you will get, and it's 105. So you have to give me the maximum path sum. It can be minimum also, the question might ask you minimum. Over here they're asking you give me the maximum path sum. Okay, so we saw that if you move from here to here, that's a left diagonal, then you move down, then you move right diagonal, you get a total sum of 105, and that's the maximum. Again, how can you solve this problem? Like, why not greedy? Because of uniformity law that I have already taught you. The values are not uniform. Yes, the values are not uniform. It might happen, I give you a value like something like 20,000, and over here from 2 you figured out 100 is the maximum, because from 2 you could have moved to 100, you could have moved to 3, you could have moved to 2. So there were 3 places where you can move, but greedily if you choose 100, the next from 100 you can move is to 1 or this to 1, so you will miss out on this 20,000. So because of uniformity, you don't know how are the values splitted across, how are the values spread across. It might happen over here there is someone very large, but on the other side there might be someone very large. So uniformity is not there, and whenever uniformity is not there, you cannot apply something as greedy, right? So what does the question state? The question state to figure out the max path sum from any cell in the first row, any cell in the first row to any cell in the last row. That is what the question is actually stating you to find, correct? So whenever there is something like a path, what do you generally try to think, like how can you solve such kind of problems? You're like, hey Striver, we're gonna try out all the paths. Again, very basic, try out all the paths, correct? You're going to try out all the paths, and if you're trying out all the paths, you take the best path among them. So how do you try out all the paths is the question. In order to try out all the paths, the only way is recursion. You go across every path, every other path, you figure out what is the sum across all the paths, and then you compute the maximum sum among them. So you have to write the recurrence. What are the steps to write the recurrence, guys? Step 1 is express, yes, express everything in terms of I comma j, express everything in terms of I comma j, and write down the base case. That's the step 1. What is the step 2? Explore all paths. Yes, explore all the paths. Over here in the question it states you can go down to the left diagonal and to the right diagonal, so explore all the paths. Then over here they're saying maximum path sum, so figure out the max among all the paths that you have explored. Figure out the max among all the paths that you explored. So if you write down these 3 points, I think you will be able to solve this particular problem. Now the question arises, you don't know where to start from, because in the other questions of grid, you know that the starting point was 0 0 and the ending point was n minus 1 and m minus 1. So you were like, okay, let's call f of n minus 1 and m minus 1 to get the answer. But over here, the starting point is not fixed, because it is saying that you can start from any of the cells in the first row, and the ending point can also be any of the cells in the last row, right? So if they're saying something like this, then there is a problem. So we need to think. So let's think. So this is the first row. Assume there are four columns, and this is the last row. Assume that there are the four columns. So I can be like, I can either start from here, from here, from here, from here, right? Or I can either end here, I can end here, I can end here, I can end here. So there can be a lot of options. Now, assuming I write the recurrence in the opposite fashion, like we write the recurrence in this fashion where we start from n minus 1, m minus 1, and we go up. Can I say we can either end, like we can either end here, we can either end here, we can either end here, we can either end here. So if I write down the column numbers and the row number, can I say I can either end at this guy, this might be the ending position, figure me out the maximum possible path sum if you end at n minus 1 and the 0th column. Or you can be like, figure me out the maximum possible path sum if you end at this. Or you can be like, figure me out the maximum path sum if you end at 2. Or you can be like, figure me out the maximum path sum if you end at 3. So you have to actually figure out every possible stuff, isn't it? So can I say if there are m columns, assuming the columns to go from 0 to m minus 1, then you have to call for every n minus 1, which is, you're saying I'm reaching every last position, and the jth column might be my ending point. So you have to call a recursion for each of, like you have to call it every time. And every time you call, remember this, every time you call f of n minus 1j, whatever maximum possible path sum you're getting, this will give you a maximum path sum, this will give you a maximum path sum, this will give you a maximum path sum, this will give you a maximal path sum, and the max of all of them will be the answer. So whenever a question states there are variable starting points and variable ending points, try to explore all the ending points or try to explore all the starting points, right? So over here we will be starting from n minus 1 and we will be going on till the 0th row, right? The generic way in which we write the recursion, start from n minus 1 and go till this. So what is f of ij signifying over here? What is f of ij signifying over here? The maximum path sum to reach ij from any cell, remember this, from any cell in the first row. Like it will automatically take the cell from the first row, but it will make sure that it reaches I comma j. So whenever I say n minus 1 0, I'm making sure it reaches here. Whenever I'm saying n minus 1 1, I'm making sure it reaches here. Whenever I'm saying n minus 1 2, I'm making sure it reaches here. Whenever I'm saying n minus 1 3, I'm making sure it reaches here. Got this? So we can say maximum path sum to reach I comma j is what I'm looking from any cell in the first row. Okay, makes sense. So we have figured out what kind of recursions will be called. Now we have to write the recurrence. So the recurrence was very simple. We will have f of ij, correct? So what is the first thing? The first thing is express everything in terms of ij because it's an grid. So we've done that. The next thing is to write the base cases. So why don't you write the base cases? Let's analyze. If I am starting at n minus 1 and I'm going till the 0th row, what did I say you in the other cases? What is generically the base case? The base case is generically the destination or out of bound cases or out of bound cases. So think, what can be the destination if I'm starting from the last row? I know there can only be a single destination, which is the 0th guy, right? So why don't you write that? So you'll be like, okay, Striver, if by chance I reach the zeroth guy, if by chance I reach the zeroth guy, then whatever is over there, yes, whatever is over there on the jth column, I'll simply return. So I have written the destination's base case. I have written the destination's base case. But what about out of bound cases? Now we are moving in the opposite fashion. Remember this. We are moving in the opposite fashion. And the question stated you can move like this, like this, like this. So if you twist it, if you like twist it, it will be, you can move in the upward fashion, you can move in the rightward fashion, or you can move in the this fashion. So there can be couple of like three different possible ways in which you can move. So thereby can I say if you're moving in the upward fashion, there will never be an out of bound case. But if you move in the leftward, you know the matrix is something like this. If you're standing here and if you move on the left, the column might go negative. The column might go negative. Similarly, if you're standing here and if you move on the right, the column might exceed the last column number. I repeat, the column might go negative, which is column might go negative, or the column might exceed the last index m minus 1. So I can say these are the couple of base cases that I have to consider. So can I say the out of bound case will come before I equal to 0? So please write this. If j is lesser than 0, or if j is exceeding the last column, what will you return? Now remember this, you are doing a maximum path sum, and I have told you whenever you do a maximum you have to return a minimum, so that the entire path gets added up to give a path sum which will not be considered. Again, recursion classes guys, recursion has to be strong. So you have to return a minimum value. So probably I'll return 1e9. I'm not returning int mean, I'll write in 1e9 because of overflow. So done, base case is done. So first step, have we completed the first step? Yes, the first step is completed. It says explore all the paths. Now how am I moving? I am moving from n minus 1 till the 0. So if I have written down this, can I say this movement is nothing but there will be a reduction in row, because if you're moving up, the row will reduce by 1. Can I say this will be I minus 1 and j plus 1? Because if you're moving up, the row will reduce, but the column will increase by 1. Can I say if I am moving left, the row will reduce by 1 and the column will also reduce by 1. So can I say these are all the paths that I have to explore, obviously. So can I say there will be a straight case, like when you move straight, thereby I can say a of the current guy, and if you're moving straight, you will have to figure out the remaining answer. So I minus 1 comma j. Perfect. So basically what I am stating is, hey listen, if you are somewhere down here, take this value, move up, and from here try to figure out what is the answer till reaching here. So this is another matrix that you're asking him to solve. You're asking him to solve this matrix. Got it? So next will be the left diagonal. So I will be like, okay, a of ij plus f of I minus 1 comma j minus 1. Again, what does this mean? If you are having a matrix and you're standing here and you move here, so you're saying from here, in order to reach the first row in this particular matrix, what is the answer? So yeah, solving, see, what you did was you took this and now you have broken down the problem into a smaller problem, and now you're solving this smaller sub problem. That is what dynamic programming generally does. Next will be right diagonal. So the right diagonal will be a of ij plus f of I minus 1 j plus 1. Again, same logic. If you are standing here and you move here, you're saying from here in order to reach here. So in this matrix, from here to here, figure me out the minimal or the maximal path sum. So I can say I will be returning the max of s and the max of left diagonal and the right diagonal. So the max of all of these three will give me the maximum path sum. So explore all the paths has been done, and the maximum among all the paths has also been taken. So again, if you carefully see, the recurrence is indeed ready. So what will be the time complexity of this particular recursion? How many paths are you exploring? That's very important. For every cell in the matrix, you're basically exploring 3 paths. So it will be like 3 into 3 into 3. How many cells are there? That is something which you have to carefully observe. The number of cells is around n into m, but if I ask you how many paths are you exploring, so it'll be like this is the length that I'm exploring, which is rather n rows. So 3 to the power m, which is near about exponential, because you'll have to take 3, then you have to again go to 3, then 3, 3, 3, 3. How long 3? For n rows. So 3 to the power n, like, which you can say as exponential in nature. The time complexity is exponential in nature. And the space complexity as of now is the recursion stack space, which is n, because at max you will travel n rows. The depth of the recursion will be n rows. So obviously this will be giving you TLE. We will have to further optimize this. And if you remember, how do you convert recursion into an optimal thing? You do memoization in this. Yes, you do memoization in this particular stuff. And how can you do memoization? If you see overlapping sub problems, you end up doing a memoization. So you can draw the recursion tree by yourself, and if you do the recursion, like over here there is a catch, the overlapping subproblems will be clearly not visible on a single call. So I'll show you that by taking a quick example. So I've taken this 3 cross 3 matrix. Now what did I say? How will the recursion work? The recursion was like, I will start from here once, I'll start from here once, and I'll start from here once, and among all of these, whichever gives me the maximum, I will be taking that sum. So I will show you the explore path option. So we see over here, we are starting from here, which is like if I write down 0, 1, 2, 0, 1, 2. So you can start from 2, 0. The left diagonal will be f of 2, minus 1. Sorry, rather 1, minus 1, because you're moving to the upward row. The upper guy will be 1, 0, and the other one will be 1, 1. So basically from here, you can move here, that's this. You can move here, that's this. You can move here, that's this. Now, this guy will be executed at first, then this guy, and then this guy. So I can say this is a out of bound case. And in out of bound cases, so since this is out of bound, this is going to return a negative value because you're looking for maximum path sum. Now what will f of 10 do? F of 10 will say, okay, I will go to my left diagonal, which is 0, minus 1. I will go to my upward, which is 0, 0. I will go to my rightward, which is f of, very important, 1, 0, 1. Okay. So something to observe over here is this. When you're at f of 10, what happens? Let's write the recursion to understand. When you're at f of 10, so it calls the left, the left diagonal, which is the current guy 2 plus f of 0, minus 1, correct? Next, it calls the upper guy, which is, again, remember this, it takes this 2 and then calls the upper one. So 2 plus f of 0, 0. Next is the right diagonal, takes the current 2 and calls f of 0, 1. So that is what it is calling, right? So what will happen with this? This guy will return 1e9. So a minus 1e9. So this entire value becomes a very, very negative value. What will happen with this f of 0, 0? So the next one is the upper one. So what will f of 0, 0 return? It will return 1 because it has reached the base case. 0 is the base case and it returns 1. So you will be like returning 1. So this returns 1, makes it a total of 3. What about 0, 1? Again a base case, so returns 1. So return 1. This will be returning 1. So in short, you will be getting 3, 3 and a very big negative value. So you return the f of 10's value as the maximum of these 3, which is 3. So this guy gets a value 3 and it returns. Now I'll erase this and you will understand the meaning of this 3 being returned. Now carefully observe, what is this 3? What is this 3 indeed? If I'm standing here and I'm saying f of 10 means this guy. From here to reach the first row, what is the maximum you can take? You can either go from here to here, which will give you 3, or you can take this path, which will give you 3. So the maximum of f of 10 is indeed 3. So I'll store that. I'll store that for the future use cases. And I'll quickly erase this off so that we have a bit more space. Now you're at f of 1 1, which means you're currently at this guy. You can move here, you can move here, you can move here. So please move 0 0, f of 0 1, f of 0 2, and again the same thing will happen. F of 1 1 will do what? It will go to the left diagonal, which is the current guy 2 plus f of 0 0. Go to the current guy plus f of 0 1. Go to the right diagonal, which is 2 plus the current guy, which is f of 0 2. So can I say f of 0 0 will return the 1, f of 0 1 will return 1, f of 0 2 will return 100. So this returns 1, this returns 1, this returns 100. So can I say over here you get 3, over here you get 3, over here you get 200. Make sense? You are getting indeed 200. So can I say the maximum is 200. Thereby this guy returns 200. So you get f of 1 1 as 200. Now you'll be like, Striver, but we are not getting a lot of overlapping subproblems. I do agree. We don't see any overlapping subproblems here, but we will see. Give me some time. Now, where are we at? We are at f of 2 0, and 2 0 means this 3 plus this guy which is 199, 3 plus this guy which is 3, 3 plus this guy which is 200, or rather 102 rather. 102. So can I say the maximum among them is 105. Thereby this guy gives you 105. So I get f of 2 0 as 105. Got this? So I'll just erase this portion. So what we figured out is, if we start from this guy, we can go to this and we can go to this, and the maximum we will get is 105 by exploring all the paths. Yes, there were no overlapping subproblems, but you can also start from 10. Yes, you can also start from 10. So why don't you start from 10? So if you start from 10, it will be 2 comma 1. So when you start from 2 comma 1, you will go to f of 1 comma 0. You will go to f of 1 comma 1. You will go to f of 1 comma 2. Now you see overlapping subproblems. F of 1 comma 0 is already solved as 3. So you can directly return. F of 1 1 is already solved as rather 102. So you'll directly return 102. F of 1 2 is not solved. So this is the only thing that you'll explore. So you see overlapping subproblems. Why? Because first you started the recursion call from here. Then you will again start from here. Then you'll again start from this guy. So when you start from this guy, all of the paths would have been solved. So this is how you see overlapping subproblems. The first recursion tree was solved. Who will have overlapping subproblems, which you can again reuse in the next call when you start from here. Again, you will start from here. So in all the columns that you start from, you will see overlapping subproblems. So that's how you can see overlapping subproblems. So I proved that you can see overlapping subproblems. And if you can see overlapping subproblems, can you use memoization? You can indeed. And how do you use memoization? You see the parameters that are changing, I, J, N and M. So a DP of N cross M will be required. So first step, you go across and you say DP of IJ. Please store whatever answer you're having. Next step, if the DP of IJ is not equal to -1, you return the DP of I and J. So in this way, you can memoize. So once you have memoized, what is the time complexity? It's a BGO of N cross M, because those are the number of states that you will have at maximum. What is the space complexity? A BGO of N cross M for the matrix and a BGO of N for the recursion stack space. You saw this is the recursion stack space. 3 length, 3 rows, 3 length is the recursion stack space. So this will be the time complexity. Now remember, the time complexity might be an N to M, but when you apply recursion, the recursion calls another recursion, passes parameters, stores everything in the stack. So it takes a lot more time than N into M. It might be N into M hypothetically, but it takes a lot more time when you call the other recursions. So thereby, this might give you tail or might not, but in a lot of places it might give you. That's why we have to optimize this. And how do you optimize this? We write the tabulation format to optimize this. So we will be writing the tabulation format now. What is tabulation? If you don't know, please watch out my all the previous videos. What is tabulation? Tabulation is something which we call as bottom up. That means we start with the base cases and then we start accommodating our answers, correct? And what is recursion? You start from the bottom, which is n minus 1, you go on till the base case, you figure out the answer, then you come back and you get the answer. So that's why that's known as top down. So tabulation is bottom up. The step 1 in writing tabulation is please write the base cases. First of all, declare the DP. It will be of the same size, by the way. Same size n and m. So please have the same size n and m. Next is write down the base case. So how do you write down the base case? Let's realize the base cases. It states if I is equal to 0, please return this. So I of j, if I is 0 rather, what can be the value of j? Think on yourself. Well, like strive out the values of j can be 0, 1, 2 and so on till the last column. So I know these can be the values, and for all of these values the value of I of j of that dp will be this. So yeah, just write it. Yeah, just write it, simple as that. So I'll be like, okay, let's write the first base case. So I know for all the j starting from 0 to m minus 1, the dp of the last row, or rather the first row of j will be a of the first row and j. That was the base case. So we have successfully written the base case. The next thing is observe the states I and j and convert to loops. So let's observe what is the value of I. What is tabulation? Bottom up. So how are you doing the recursion? The recursion is going from n minus 1 to 0. So the bottom up will go from 0 to n minus 1 because the base case is 0. But you have already solved for 0. So you'll just start from the next case, which is I will start from 1 is to n minus 1. Why? Because you have already solved the case for 0. So you start from the next guy, the bottom, the base case is covered. So you move to the next bottom, which is 1. So I is explode. So just write the first loop. Simple as that. Don't complicate. Just write the first loop, which is from 1 to n minus 1. Written. Next, there is another state which is dependent. So the state j is dependent on I. For a given I, what can be the possible values of j? Just figure that out and you'll be able to solve this problem. I can say for I equal to 1, j can be 0, 1, 2 till m minus 1. For I equal to 2, j can be 0, 1, 2 till m minus 1. For I equal to 3, j can be 0, 1. So for every possible I, so can I say for every possible I, the values of j will be from 0 to m minus 1. Again, makes sense. For every possible I, that will be the values of j. So just make sure you write that in another loop. So j will be from 0 to m minus 1. And that's how you can easily conclude your couple of loops. And once you have written the loop, just copy paste the recurrence. So what was the recurrence? So you can see this on the screen. The recurrence was, there was an uppercase which stated a of I j plus, instead of f, it will be dp of, what was the case? As the previous case, I minus 1 and j. So just write it. The left diagonal was, you just took a of ij. Again, instead of f, you write dp of I minus 1 and j minus 1. Again, instead of the right, you write a of I of j plus dp of I minus 1 and j plus 1. So just write down all of these three, and what you can do is you can write dp of ij similarly as max of all of these three, u, ld and rd, the right diagonal. And once you have written this, you remember what were the answers? The answer was, so we have almost figured it out, but will this work? No. This will give you a runtime error. Why? Because if you remember, we have solved the base cases, but if I take you back to the recursion, there was something as an out of bound case where you might run out of bound. So just make sure, yes, just make sure for this j minus 1 you write an out of bound case, for this j plus 1 you write an out of bound case. So can I say if j minus 1 is greater than equal to 0, then only the left diagonal will be possible? Or can I say if the j plus 1 is lesser than m, then only the right diagonal will be possible? So you can just write it. I'll show you that in the code while I code it. But yeah, you can just easily write it over here. So this is how you can do it. Now if you remember, the recursion calls were made from f of n minus 1 0, f of n minus 1 1, f of n minus 1 2, and so on till f of n minus 1 and m minus 1. And out of these, the maximum, yes, out of these, whichever value was the maximum, you said this is my answer, correct? So over here, how will you do it in the tabulation form? In the tabulation form, probably you can keep the maximum as dp of n minus 1 0, that's the first column, and then you can start from the next column till the last column, and you can say max c, you can keep this as maxi, comma dp of the last row rather, comma the jth column. So if you just do this, whatever answer the maxi will give, yes, whatever answer the maxi will give will be your particular answer. So this is how I've converted this into a tabulation format. So if I can say how the tabulation format going across the time complexity, big O of n cross m plus another big O of m, you can say, for computing this particular stuff. Space complexity, no recursion stack space, just an n cross m. So this is what, yes, this is what the tabulation time complexity and the space complexity will be. Still now there is a chance of optimization, that is in terms of space. So I told you, if you remember, I told you, whenever you see I minus 1, I minus 1, I minus 1, there can be a space optimization. The concept of previous that I have already taught you. So why don't you apply the concept of previous? So can I say how is this working? Like, how is this loop working? First of all, you're filling the base case, right? So assume these guys are getting filled in the DP array, right? Then you're starting the loop from I equal to 1. You're starting the loop from I equal to 1. So you're basically going and filling up the next row. And when you're filling up this guy, you're basically saying the upper is this, the right diagonal is this, and the lower diagonal is not here. So you're taking this guy and this guy in order to have, like, what are you writing basically? You're writing dp of I minus 1j, dp of I minus 1j minus 1, and dp of I minus 1j plus 1. So you're taking the previous guys, right? And you're filling this. Next, when you're trying to fill this, in order to fill this, you're saying I minus 1j minus 1, I minus 1j, I minus 1j plus 1. Next, you're going across and filling this. For this, you're taking this guy, and this guy. Next, for this, you're taking this guy, and this guy. Correct? This row will be filled. And the moment this row is filled, the value of I increases to the next. And now you start filling up this guy. And in order to fill this, you'll just require this and this. So, do you need to store this? No. You just need to store the previous row. So just keep on storing the previous row. Like, first you would have stored this previous, and then you computed this current, right? Next, when I reaches here, this current will become your previous, and you can just easily compute the current. And again, when you move to the next I, this guy will just require this guy, and this will become the previous, and again compute the current. So at the end of the day, the last row that is left can easily be used to find the maximum. Like, you can figure out the maximum of all of these last rows, and that will be your answer. That's how you can space optimize it. So what you can, in order to space optimize this, what you can do is, you can declare a previous of size n, you can declare a current of size n, right? That's what you need to do. And over here, instead of dp of I minus 1, you can say previous of I minus 1j, previous of this, and instead of dp of ij, you can say cur of j. And whenever this for loop is over, the cur will become the previous for the next I. So the previous will be now the cur. So in this way you can do it, and just to make sure, this guy will be now the previous of j. So that's how you can just space optimize this. Whenever you see I minus 1 something like this, you can always space optimize this. So once you space optimize this, the space complexity now boils down to big O of n. Like you're just using couple of rows, like one to store the current and one to store the previous. You're not using n into m rows. So that's a lot of optimization that you are doing. So it's time to code out so that you also have a quick revision. So first I'll just take the size. Let's quickly take the size. So the matrix of 0 dot size, correct. And then we can definitely write a function which will be int I, int j, and probably we can just carry on this vector. Just make sure you carry on this vector. And right over here, what can you have is, one of the base cases is this. That's everyone knows this. This is one of the base cases. There is one out of bound case, which is this, correct. Or if it goes like matrix, okay, 0 dot size. So that's one of the bound cases. I can say 1e8. I'll return a very small value. I know there'll be an up, which will be matrix of ij plus f of I minus 1j and comma matrix. And there will be a left diagonal as well, which will be matrix of ij plus f of I minus 1 and j minus 1 comma matrix. So you can definitely write that off. There will be a right diagonal as well, which is matrix of ij plus f of I minus 1 comma j plus 1 comma matrix. And at the end of the day, you are going to return the max of up, max of left diagonal and the right diagonal. And over here, you have to call from all of these guys. So you can keep the maximum as very small number. And you have to call from all the columns of the last row. So just call from all the columns of the last row. Very simple. So can I say this, that if max c equal to max of max e comma f of n minus 1, that's the last row, and the column j and the matrix? Yes, you can. And over here just have a maxi and you can return maxi, correct. So if I just run the code, you will see, I think this should be fine. Yeah, it does run, but it will give you a TLE because it is the recursive solution. So what you just need to do is please create a vector dp. So I'll create a vector dp super quick. So once you create the vector dp, just make sure you pass it across over here. So just pass it across over there. That'll be the same one. Just copy paste, and this will go as dp now. And over here, just pass on the dp, pass on the dp over here, pass on the dp over here. And once you're done with this, next step, please make sure store the states. For the next step, just make sure if a dp of ij has not been previously visited, you return that dp of ij. And I think we should be running fine. Let's quickly run this off. Does run. Let's submit this. So if I submit this, I am getting an absolutely correct answer. So it's time to convert this recursive into a tabulation format. So this will definitely be 0. And I'll just make sure I keep some space over here. And I know there will be the base case, which will be like j columns. So why don't I write the base case as dp of 0 and j equal to matrix of 0 and j. And I know it was something like I equal to 1 goes till I plus plus. And I'll go from j equal to 0 till j lesser than m and j plus plus. And why don't I copy paste the same thing? Yeah, just copy paste the same thing. So if I just copy paste the same thing, should be absolutely fine. And what I'll do is, instead of this, I'll write dp of I minus 1 and j, and I'll omit this portion. Over here, I'll make sure I will write dp of I minus 1 and j minus 1, and I'll omit the remaining portion. Similarly, over here, I'll write dp of I minus 1 and j plus 1, and I'll omit the remaining portion. So once I have written this entire portion, I can say dp of ij will obviously be equal to the max of all of these three. So I'll just write this off and just make sure this plus, yes, this plus will only be possible if it's not. So I can say if j minus 1 is greater than 0, then only you add this in LD. Otherwise, you can omit this by adding a very, very small number. As simple as that. Similar to the out of bound case. And similarly, you can say over here, like, similarly, you can say over here, if j plus 1 is lesser than m, then only you should add it to the RD. Otherwise, you can easily omit this path by adding something as 1e8. So again, the same thing will happen. Now over here, instead of n minus 1, you will say dp of n minus 1 and the j's. Simple. And let's omit this off. And I can just return the maximum. So let's quickly run this off and see if this is running fine. Okay, we see some cases. Okay, looks like I've missed some syntax errors. Cool. I'll just quickly correct this off. So you see I have corrected this, and now if I submit this, it should be running fine. Yeah, it does run fine. Next step, space optimization. So instead of this, what do you need? You need a previous of size n cross 0, sorry, rather m cross 0, because there are m columns. You need a current of m cross 0. And instead of dp of 0j, it will be previous now. Instead of dp of I minus 1j, it will be previous now. See how simple it is. Super duper simple. Previous. This will go as previous. Done. Instead of dp of ij, it will be cur. So once this is done, you can say this will be nothing but the cur will go as, sorry, the previous will be now cur. Previous will go as cur. And over here, instead of a dp of n minus 1, because that is stored in previous and current both, so you can just do a previous of j, and again you can run this code. So you see I've omitted the dp array, and if I submit this, this is also going to work fine. Yeah, it is. So this is how I can space optimize this. So guys, I hope you have understood all the 4 approaches: recursion, memoization, tabulation, and space optimization. So just in case you did, please make sure you like this video. And yeah, to follow our tradition, if you have understood this, please do comment understood. Please do comment understood, because that is the only thing that keeps me motivated, that whatever I am teaching, you are understanding. So with this, I'll be wrapping up this lecture. Let's meet in the next one, where we will be discussing the next problem from the dynamic programming playlist. Till then, bye bye, take care.
Whenever your heart is broken,